This is a real NASA heat shield demonstration. A blowtorch heats the front of a black sandwich panel until one spot glows red. Then an engineer puts his bare hand against the opposite face. Still feels cool. This sample is not the flight shield, and NASA's transcript says the tabletop test reaches only a few hundred degrees Fahrenheit, not the 2,500 degrees the real spacecraft is built to face. But the temperature split is genuine. The same design idea lets Parker Solar Probe put one side near a star while its electronics stay close to room temperature. So where does the heat go, and why does it not cross these few inches? Parker Solar Probe dives through the sun's outer atmosphere and, at closest approach, moves about 430,000 miles per hour. The corona can contain particles at temperatures of millions of degrees, but temperature alone does not tell you how quickly something heats. The corona is extremely thin. For Parker, the brutal load on the shield comes largely from intense solar radiation. NASA says the sun-facing surface can reach roughly 2,500 degrees Fahrenheit, while the spacecraft and instruments inside its shadow stay near 85. That difference is not refrigeration magic. The shield controls three things at once: how much energy enters, what survives the energy that is absorbed, and how slowly that energy can travel toward the spacecraft. The flight shield is about 8 feet across, a little over 4.5 inches thick, and weighs only about 160 pounds. Its outer faces are carbon-carbon composite. Between them is a thick carbon composite foam core that NASA says is 97% air on Earth. On the sun-facing side, a specially formulated white coating reflects as much incoming energy as possible. Even the mounting points matter. The shield connects to Parker's truss at only 6 points to limit paths for conduction. So this is not one miracle substance. The front reflects energy. The carbon faces tolerate high temperature. The foam traps long, poor pathways for heat. And the small attachment area reduces the number of bridges leading into the spacecraft. Watch the sample again. The torch pours energy into one small area. That front spot absorbs enough energy to glow, but heat still needs time and a conductive path to reach the back. The carbon foam core is intentionally bad at passing heat. In space, there is another advantage. No surrounding air means no convection carrying hot gas around the shield and onto the spacecraft. Radiation still matters, which is why the reflective coating faces the sun. This is the difference between temperature and heat transfer. Oven air can be hot enough for your hand for a moment, while the metal rack at the same temperature burns immediately because it transfers energy much faster. Parker's shield is engineered to make the dangerous direction of heat flow extremely slow. The disk only protects what stays inside its shadow. 7 sensors sit around the shadow's edge. If sunlight reaches one, Parker's computer can correct the spacecraft's pointing without waiting for commands from Earth. Its solar arrays must peak beyond the shield to make power, so they retract near the sun and circulate about a gallon of deionized water for cooling. Some sensors deliberately extend into the hot environment and use their own high-temperature materials. NASA also tested the spacecraft in a giant thermal vacuum chamber, but that was a different test. It reproduced airless hot and cold cycles, not the full 2,500-degree solar load. Engineers split the problem into separate tests because no single room can reproduce every hazard at once. The blowtorch clip is more than a stunt, but it proves something precise. It does not show that the shield never gets hot, and it does not make flight hardware safe to touch. It shows that a severe temperature difference can exist across a very thin, lightweight structure when reflection, high-temperature surfaces, and low conductivity work together. By keeping its heat shield pointed at the sun, Parker Solar Probe can sample a star's atmosphere while most of the spacecraft remains in a survivable shadow. When you see flame on one side and a bare hand on the other, the hidden clue is not that the material defeats heat. It controls where the energy goes and how long it takes to get there. Subscribe for more real tests decoded from the first frame.